Hello, I am Kamal Askar from Professor Stephen Ringe's group, Digis, South Korea. We will present multi-scale design of copper catalyst for electrochemical reduction of carbon dioxide. As we know that increasing concentration of carbon dioxide in the atmosphere because of extensive use of fossil fuels across the world. Therefore, the electrochemical reduction of carbon dioxide into mono and multi-carbon products is a promising approach. For this purpose, we have developed a multi-scale computational approach to optimize the electrocatalyst, that is copper 211 in our study. Because copper-based materials show significant selectivity of CO2 reduction reaction towards C2 products in addition to C1 products. Multi-scale modeling consists of microkinetic region and mass transport region. Using the microkinetic modeling package gate map, we evaluate the turnover frequency of all products as a function of CO2 partial pressure and pH. The original microkinetic model was developed by Karen's group, and we just simplified this model based on some important reaction intermediates. And this is the reaction mechanism scheme of CO2 reduction reaction towards C1 product and C2 products. And this is the hydrogen evaluation reaction mechanism scheme, which is a competing step in CO2 reduction reactions. All reaction energetics were obtained by using DFT calculations. And for adsorbate interaction, we use first order expansion. The charge extrapolation scheme was used to find electrochemical reaction barriers. Figure 2 represents microkinetic modeling of carbon monoxide coverage and ethanol turnover frequency, both as a function of partial pressure and pH. We can see a different voltage, different coverage, and different turnover frequency were observed. Figure 2 shows experimental and simulated polarization curves. We can see that our simulated polarization curves are qualitatively and semi-quantitatively in good agreement with the experimental curves. At higher order potential, depletion in C2 product was observed, but no depletion was observed for C1 product at higher potential. This is the simulated and experimental HGR. Both are in good agreement. And this HGR current density is obtained by fitting the Harris-Key actuation barrier to reproduce the experimental turn of HGR current density.
Hello, I am Aditya Abi from Professor Stefan Renge's group in DG South Korea. So in order to develop the multi-scale model for planar copper system, we used the microkinetic model, which was put in figure 2 and converted it to a text file and gave it as an input into COMSOL multi-6 finite element program package. So using the multi-scale model, which was developed in Ringe et al. Paper for the planar gold case, we used the microkinetic model functions into it and coupled it with the mass transport functions in the paper and developed the multi-scale model for planar copper system. So we compared the current density values obtained by simulations from multi-scale model and microkinetic model with the experiments for C2 and C1 products as shown in figure 4b and 4c. The limitations in current density values for the multi-scale model shows the inclusion of mass transport effects into the model, and the data seems to be in good agreement with the experimental data. Our ultimate aim is to develop a gas diffusion layers electrode setup, as gas diffusion electrode enhances mass transport and improves current density up to 360 milliamp centimeter square, thus increasing its prospects for commercialization. The gas diffusion electrode consists of 3 parts, which is the gas diffusion layer, the microporous layer, and the catalyst layer. So the gas from the gas chamber goes into the gas diffusion layer, diffuses into the microporous layer, and finally dissolves into the liquid electrolyte and is activated during CO2 electrode reduction process. There are two cases in this. One is the flooded case and the other is the wetted case. In case when the catalytic pores are completely occupied by the liquid electrolyte, it is a flooded case, and in the wetted case, there is partial occupation by the gaseous phase and the liquid phase. So using the Weng et al. Paper, which reports 20 model for gas diffusion electrodes for CO2 electrode reduction purpose as a basis, we developed this 2D model for the flooded GDL as shown in this figure. The figure contains appropriate transport equations in appropriate domains along with the boundary conditions of the boundaries. So basically, we are solving the Nernst-Planck equation at the catalyst layer, the electron neutrality condition as a constraint, and we have obtained concentration profile values up to minus 1.3 volts versus SHE. The concentration profile values obtained show a perfect match with the data reported in the 1D model. We are further working on it and looking to compare the results with the experimental data. So to conclude our results, we present a refined microkinetic model you developed using CatMap and a multi-scale model developed using COMSOL multi-6. Microkinetic model reports turnover frequency as a function of CO2 concentration, pH, and voltage, and we are about to implement a 2D model to study the effects of flow rate, gas composition, and electrode assemblies. We are looking to improve the model and compare the results with the experimental data. Thank you for your attention.